Lupin Pharmaceuticals in association with Higher Secondary Principals Forum.
Hello students, today we will be discussing one important topic of our 12th standard syllabus. The topic by name, as you see on the screen, differentiation. Also mentioned in the bracket, derivative of a function, because finally it is the process of differentiation of a function, and so it is called derivative of a function. Now, not that we are not aware about this particular topic, isn't it? Because you had the same topic also marked in 11th standard syllabus. But let me today try to help you all in knowing how exactly we dealt with the topic in 11th standard and how exactly are we going to go about the topic in 12th standard. So therefore, to help you all in just recollecting, when the topic was taught in 11th standard level, we just learned the basic definition of the topic, the concept differentiation. We learned how to derive the formula of differentiation for some basic functions, isn't it? And there we learned something about first principle of differentiation. So it was only this much of part of differentiation was taught in standard 11. Now it is that we have to now skillfully use this knowledge of 11th standard now to deal with some important concept of differentiation in 12th standard. So that is how we go about with the topic differentiation. So see, imagine how interesting it will be now for us, because see, we will be now using or applying all that we learnt in 11th standard for understanding something new of differentiation. Isn't it going to be very interesting, you think? So therefore, I am today going to teach you all some important interesting concepts of differentiation. But before that, I personally feel that recollecting something that we did in 11th standard is must. So therefore, let us at a glance try to recollect or see, view some of the important concepts which we dealt with in 11th standard. So just to help you all in recollecting, when we talk about differentiation or derivative of a function, we know that if there is any function given to us denoted by y equal to f of x, meaning if I have y variable defined as, just taking an example, say 3x minus 5, wherein there is a function or an expression defined using two variables, we have x as well as y, where you see that the variable y is defined in terms of x, and thereby we called x to be an independent variable, y therefore was called a dependent variable, and therefore we learned in 11th standard that since y solely depends upon the variable x, obviously any change in the variable x obviously will bring about the change in the corresponding variable y, which depends upon the variable x. So therefore, measuring this difference in the variable y occurred due to the difference in the variable x was what is called differentiation or derivative, and we denoted it by dy by dx. And we also related this particular concept with the geometrical aspect of it, and therefore we learned the geometrical meaning of this. We learned that what dy by dx actually, in a simple manner, since it is difference between of the variable y with respect to the difference in the variable x, we also call this geometrically it meant the slope value of the tangent drawn to the curve. All this was done in 11th standard, and thereby we learned one important formula or the method for finding differentiation, and we learned that the derivative value of any function at any instance can be calculated using the formula limit h tending to 0 f of x plus h minus f of x divided by h. And therefore, we tried using this formula for finding the derivative of many functions to help you all in recollecting, and thereby we had that entire list of formulas derived What kind of formulas? If you just see the important basic formulas we learnt last year, it was this important set of formulae. Which are the formulas covered in this particular list? If you see right from the first, if it is derivative of x raised to n, we called it nx raised to n minus 1. All the important formulas of the form constant is 0, kx is equal to k, then the derivative of root x 1 upon 2 root x as you see. Then the whole list of 6 important trigonometric functions as you see. We derived all this by using the very first principle of differentiation. Then we also saw about exponential cases. We found that derivative of e raised to x was e raised to x, that of a raised to x was a raised to x into log e. Just helping you all in recollecting what was taught in 11th standard, and therefore we prepared this important list of the formulas if you are aware. Now please remember that all this knowledge of important formulas is to be used now in 12th standard, and just cannot forget about the important part what we call as algebra of differentiation. Now what exactly did we learn in algebra of differentiation? It is in the part algebra of differentiation. We learned that if I have a function, trigonometric function given by y equal to sin x, whose derivative very well known from the list which I presented just now as cos x. If there is another function taken as y equal to e raised to x, whose derivative we know is equal to e raised to x. But imagine if there is a third function constructed by skillfully combining these two forms. In the manner, if I now define a third function as y equal to sin x plus e raised to x. Now what have I done here in constructing this new function? The simple thing, I have used an algebra of addition. So I have constructed a new function by adding these two functions. So therefore, if there is a time now finding the derivative of this new function, how do I differentiate this new function now? It is here that I will have to have the knowledge of algebra of differentiation. There has to be a certain proper rule, isn't it? So I cannot simply differentiate it in any manner. There has to be a perfect rule. And all these perfect rules are taught to us in this algebra of differentiation. Now what exactly does this algebra of differentiation has to tell us? Now if we just view, the first algebra tells us that if I have to now find the derivative of, just compare this example with the first algebra which you see. If I have my value of y or the function defined as the addition of two functions, then it is my algebra there to help me in differentiating this function. My algebra of differentiation tells me that my value dy by dx therefore has to be equal to, so if it is y equal to f of x plus g of x, then the derivative of this addition also has to go in the same manner as you see there in the right hand side. It says the differentiation also has to be in the same manner, meaning my derivative will be equal to derivative of sin x, which I know to be cos x, plus the derivative of e raised to x, which I know to be e raised to x. So therefore here, so as we see, if I am given the value of y in the form of addition of two functions, it is my algebra which tells me the method of differentiating the function. The algebra rightly tells me that the derivative also has to go in the same manner. Also imagine if I have to have the subtraction of two functions, then what exactly will it be? Again the algebra to tell us that the derivative also will move in the same manner. But be very careful or be little alert, as you all know, if I have my function defined in the form product of two functions, like if I am given y equal to sin x into e raised to x, then we know very well that the differentiation doesn't go in the manner how it was with addition and subtraction, isn't it? Because when I have my value of y or y function defined as the product of two functions, then here is the algebra which tells me that the derivative therefore should be equal to, as you see rightly defined, the first function into the derivative of second plus second function into the derivative of first. So therefore students, you should be very well, understanding the difference, how tactfully these algebras have to be used. So therefore, though they were very simple for the first two cases, certainly not for the third. And therefore, if I have this product form for differentiation, then as you know, the derivative will be equal to, as I am rightly using the algebra, the first function as it is into the derivative of the second function, where I know that the derivative of e raised to x is e raised to x, plus the second function to be now kept as it is, to which now we multiply the derivative of the first function, where we know derivative of sin x is cos x. So here is my differentiation value. Likewise, just to help you all in recollecting, if I have another form, suppose defined as say e raised to x upon sin x, I am taking the quotient form now. Then my differentiation, again the algebra has to tell me let the derivative of quotient form therefore will go in some other manner. Now what is the formula? The formula says my derivative will be equal to, so my dy by dx value will be equal to the denominator function to be kept same, multiply the derivative of the numerator which we know is e raised to x, minus the function in the numerator multiplied by the derivative of the denominator, that is cos x, divided by square of the denominator, sin x the whole square. Students, please remember, I am just helping you all in recollecting what was taught in 11th standard, and just see, we just cannot overlook at this particular part, because we do require this now when we will be dealing with 12th standard concepts. Okay, so just in a way helping you all to just recollect in mind like what was taught in 11th standard. So this was all taught in 11th standard. So therefore now you all must have understood that when we have to now learn about some new concepts of differentiation, the differentiation never can happen without having the knowledge of formula of differentiation and algebra of differentiation. These are the important components, okay, of differentiation. But it is this knowledge which has to be rightly used now for understanding the important concepts of 12th standard. Now what exactly, now I am actually coming to the concepts which you will find marked in 12th standard syllabus. Our syllabus begins with the first important concept, teaching us how to differentiate something called as composite function. Hearing for the first time about composite function. So therefore, if I have to teach you how to differentiate composite function, certainly I will have to spend some time here in making you all understand the meaning of the term composite function. So therefore, let me take some time here in explaining to you the meaning of the term composite function, and once we get acquainted with like what composite functions are, then in a step, the next step, I will teach you all the method of differentiating these composite functions. So now it is the differentiation of composite function, and therefore an attempt here to make you all understand the meaning of the term composite function. So therefore, what exactly are composite functions? See, to make you all understand, the simple definition I would like to define it as, I would say, any function defined by combining two or several functions is what exactly is called composite function. Example, say for instance, I have one function defined as f of x equal to sin x, and I take another function denoted by g of x equal to e raised to x. We know them well. One is a trigonometric function, another one is a exponential function. Now say for instance, if I have to define a composite function, as I said rightly, composite function would be the combination of two functions. So therefore, if I now decide to design a composite function by combining these two functions, I have two ways of combining them. Like one thing, what I can do is when I am constructing this new function, I may denote it by h of x. In a simple manner, what I can do is, I can construct this new function either by inserting the second one into the first, or I may design the function by inserting the first function into the second. But where exactly the insertion will be? Now say for instance, I have decided to prepare the composite function by inserting second one into the first. So this insertion exactly has to happen in place of the variable x. So imagine if I have to now design the third function, my h of x function will be equal to sine of inserting the second function into it in place of the variable. So it will be this. So this new function which I have constructed by combining the two functions is what we call as the composite function. I can have another composite function. Now the insertion will be other way around. So therefore, if I call this function say p of x, I would now try inserting the first function into the second. So therefore, my new function p of x will be e raised to, but I will see that the insertion is happening here in place of x. So therefore, it is the first function which will go in place of x. So will be e raised to sine x. See how beautiful it looks. So the first function, combination of the two functions, also the second one, combination of two functions. These are what we call are the composite functions. And if we have understood what a composite function is, let us therefore in the next step learn the method of differentiating this composite function. So say for instance I have the first function. Now please remember that the differentiation of composite function has to always happen using a rule known as chain rule. So the rule called chain rule. Now what exactly the chain rule has to say is, like how in the chain we have different segments attached. So therefore the differentiation also has to happen as per those segments which are seen in the chain. Say for instance I have this particular function. If now I have to differentiate h of x, as you know the derivative of h of x can be denoted by h dash of x. My derivative will be equal to, what I will do is I will look at the composite form and I will decide the segments or sequence how my function is. Now in the sequence, as I notice, the first function I come across is the sine function. So my function for differentiation is sine function. But what is sine of? So now I am coming across the second segment. So it is sine of e raised to x. So I have rightly understood the two segments in the chain. So the first one is the sine function and the second one is e raised to x. So my differentiation as per the chain rule also has to go as per the same sequence. So when I find the derivative of this composite function, the first function I am coming across is sine function whose derivative we know is cos. Correct. So derivative of sine is cos. So I am going in sequence. So the first segment, it is just the differentiation of the first function. The second bracket which you see e raised to x will remain as it is for this part. So since we know from the identity that derivative of sine is cos, so that is why derivative of sine of e raised to x has become cos of e raised to x. Now to this I now multiply the second segment. Now what will go into the second segment will be the derivative of the second function in this sequence. Now what is the second function identified in the sequence is e raised to x. So I now multiply this by the derivative of e raised to x, which we know is e raised to x. I have completed the entire sequence and therefore is the end of differentiation. And that is how my differentiation value would be this. Let us also try the same thing, doing the same for the second function which I have constructed. Again a composite function. So if I have to now write the derivative of this composite function, I will call it p dash of x is equal to, I have to rightly understand the sequence as I told you all. So when I read the function, I read it as e raised to sine x. So I know that I am given an exponential form. So it is e raised to exponential form. So the first part in the differentiation will be the very derivative of exponential term. To this I should multiply. So the chain continuing. So to this I should multiply the second function in the sequence. What is the second function in the sequence? Is the trigonometric function sin x. So the derivative of second function should go in the second bracket. Let us now try to fill the boxes. So the first bracket here. Derivative of every exponential function, as we know, is the same exponential function. So if I have e raised to sine x, the derivative of e raised to sine x from the previous formula we know is the same, e raised to sine x. So done with the first form. But as per the chain rule, what I have to do now is I have to differentiate the second function which is there appearing in the sequence. The second function in the sequence is sine x. The derivative of sin x we know is cos x. So we'll go in the second bracket, that's it, is my required differentiation value. So this is exactly the way how we differentiate the composite function. But please remember, now that we have seen how individually how the composite functions have to be differentiated. But imagine if I have to write a case here for you where my function suppose is defined as, if I have f of x defined as say root of sin x plus e raised to 2x. Say for instance you get this function for differentiation. Then don't forget, as I told you all, the very basic thing that we do in differentiation is always the first thing which come on priority basis is nothing but the algebra of differentiation. So what I will have to do is, when I am looking at this particular case, I will rightly see in what manner the function is appearing. It is nothing but the addition of two functions. So it is the same old algebra of differentiation, therefore will tell me that the derivative of this will be equal to, as per the algebra, derivative of the first function plus derivative of the second function. So therefore now please understand how important the algebras of differentiations are. So not that on a way when you are proceeding ahead learning new techniques of differentiation, old things cannot be forgotten. Because rightly the differentiation, the very basic thing in differentiation requires the knowledge of algebra of differentiation. So the differentiation will be equal to, as per the algebra of differentiation, derivative of the first function plus derivative of the second function. But when in turn when you will be calculating, measuring or finding the derivative of the first function, there you all will realize that it is a composite form. Because if I see this, I will call it a root form. The derivative of root. So therefore the first function in the sequence identified to be root form. The second function root of, so the second function in the chain is sine function. So when I write the derivative of the first term, the derivative as per the derivative of the formula known, derivative of root x is 1 upon 2 root x. So the derivative of root sine x will be 1 upon 2 root sine x. But then as per the chain rule, we multiply this by the derivative of sin x and is cos x. Follow the algebra. So the plus sign will remain the same. Now comes the derivative of the second function. The function is e raised to 2x, no doubt, but the sequence, the first form we have, the basic form for differentiation is exponential form, but do not forget is also combined with 2x. And therefore my differentiation here, derivative will be e raised to 2x, as we know is the same, e raised to 2x, but without fail multiply this by the derivative of 2x, and that is 2 will be the required value of dy by dx. So therefore if you see two things we have done here, we have certainly calculated the derivative applying proper algebra of differentiation, but individually if we saw, the derivative of each term was nothing but differentiation of composite form. So after completing the concept differentiation of composite function, we are now here to learn another second important concept in the topic called derivative of implicit function. So again spending some time here in making you all understand the meaning of implicit function. So once we understand what implicit function is, then the time could be spent on understanding the method of differentiating implicit function. Okay, so therefore let us first try to understand the meaning of what we call as implicit function. Now students, if you just try to recollect the examples which we were solving all this while on differentiation, if you just recollect, the examples were all defined in this particular manner. So if I have one example as y equal to sin x given for differentiation, of course, the question is to find dy by dx. If I try also writing few more, say y equal to 3x cube plus 5x minus 6 and several others. And if I now write a third important case for you, say the case here is x square plus y square equal to 16. Again the question remaining the same, find dy by dx. Now if you just compare the first two forms with the third form which I have presented here, the question remaining the same, given y equal to this, given y equal to this, given x square plus y square equal to 16. Question is to find dy by dx. I'm quite sure it's quite easy for you all to notice the difference, okay, the difference skill which I have used here in stating the example. Like if you see the first two cases presented, they look more or less similar. Similar in the sense, at least the pattern used for defining the functions is the same, isn't it? But certainly not the same pattern used for defining the third case. Now what is that basic difference which you see here in the first two cases and the second case here is that if I talk about first two cases, no matter all three cases here are defined using the same two variables x and y. But see the difference here. In the first two cases, if you notice, while writing the expression, I have seen that it is always the variable y which is always kept to the left side, and the variable x is used throughout over the right hand side, isn't it? So that is the common pattern that I used in writing the first two cases. So you can say, you know, the y variable is always exclusively given the left hand side, whereas the x variable is exclusively given the right hand side. So they are, you know, like there is a demarcation. Y stands on this side, x on the other side. Now this pattern of writing the function where you have y variable on one side and x variable being used over the other side, these kind of functions are called explicit function. So if you look at the first two functions which I have written for you, they are the examples of explicit function. But look at the third case. If I see where is the variable x, where is the variable y, you find them all, you know, mixed together. Like I haven't given them a proper side, not that, you know, one variable is on one side, other one is on the other side. No, like you can see them used combined. Like, you know, even other example if I produce, say x square plus xy plus y square equal to say 5y. Do you find, you know, any kind of demarcation here as far as variables are concerned? Certainly not. They are all going in a mixed form. So this way of representing the function is what we call as implicit function. So what an implicit function is? The function defined combining x and y together is what we call as implicit function. So here are the, so therefore if we just compare the first two cases with the other two cases which I have written, it would be very easy for you all to understand the difference between the two. So therefore remember that these two forms are of explicit cases, whereas these two forms which you see are what we call as implicit functions. So today in this session, we are now going to understand how exactly do we differentiate the implicit function. How do we differentiate the explicit function? That we were doing all this while, isn't it? All that we did all this while was nothing but we were learning the technique of differentiating explicit function. But it is now for the first time we will be learning also how to differentiate implicit function. Now how exactly? So the basic technique that we use while differentiating implicit function is, we will try to make it more easy by means of examples, but certainly just for you all to remember, okay, the technique, the basic technique which goes here in differentiation is, when I have any implicit form given for differentiation, it is only that the terms, when you are differentiating, the differentiation has to go term wise, how the terms are given, and the final answer for dy by dx has to be obtained by bringing all dy by dx terms on the left hand side of the equation. Okay, probably this may not, I mean, just try to relate this with the examples when we solve, so that it will become more clear to you. So therefore now let us try by means of some examples, like how exactly to find the value of dy by dx if we are given some implicit for differentiation. So therefore we just now learnt the meaning of implicit function. So if we now know very well the meaning of the term implicit function, let us now learn the technique of differentiating this implicit function. Okay, taking one simple case here for you all to understand the technique used for differentiating implicit form. Say I have the form x square plus y square equal to 16. and I am given it as in the form of implicit manner, isn't it? Now see, not that this cannot be converted into explicit form. I can very well try converting this into explicit form, but I will not do so because I know that continuing in the same manner would be more convenient. So let us continue in the same way. So I have a function x square plus y square equal to 16, and as you see the variable x, y all together. So therefore this is the implicit form given for differentiation. Now what will be the question stated? The question will be to find the value of dy by dx. Now just some attention here on this important part that I am explaining. Now all this while we have learned that the whole process of differentiation is nothing but just playing with the variable x and y, isn't it? So therefore what we learned so far is, say for instance if I am given a function sin x, now a function defined in terms of variable x, and suppose if I am asked to differentiate this function with respect to the variable x, or if I am asked what is the derivative of sin x with respect to the variable in terms of which it is defined, like sin x is defined in terms of x, and if I am also asked to differentiate it with respect to the same variable, then my immediate answer to this will be cos x. If I am asked what is the derivative of e raised to x with respect to the same variable x, then my immediate answer will be e raised to x. What is the derivative of x square with respect to the same variable x, my immediate answer will be 2x, isn't it? So therefore meaning when you have a function defined in terms of variable and you know that you are differentiating also in terms of same variable, the immediate answer is all by following the list of the formulae. But now a small twist. Imagine if I have a function here defined as sin y. And if now see the change, I have taken a function defined in terms of y, but my question remains the same. Meaning I am told to differentiate it with respect to x. Previously the function was sin x. I was asked also to differentiate it with respect to x. The corresponding derivative was written as cos x. But now to understand the difference, I have the function defined as sin y, so the variable has changed, but the differentiation asked is again with respect to x. Now how do I tackle this? So what we have noticed majorly here is that there is a change in the variable. So therefore now what you see is the function is the same, the variable has changed, but the differentiation asked is with respect to the same variable, with respect to x. Now how do I tackle this? Now please remember, if I have this kind of difference seen, that the function defined is in terms of one variable, but the differentiation is asked with respect to some other variable, then the differentiation has to happen as per the chain rule. So therefore what I will do is I will treat this as my composite form now. Sin therefore will be taken as the first form for differentiation, composite form. So I am going back to the previous form discussed. So sin therefore would be the first form, y would be called the second form in the sequence. So when I am writing the derivative of sin y with respect to x, the derivative of sine function, the first function sine function in the first bracket will be cos of y, but to this we shall multiply the derivative of the second function. What is the second form here in the bracket? Y. So the derivative of y with respect to x, which we know is dy by dx. One more example for understanding. Say for instance I have x square, and if I have to write the immediate derivative of this with respect to x, I will write the corresponding derivative as 2x. But now if suppose I have the function defined as y square, and I am asked to differentiate this with respect to x, now that I notice that the variable has changed. Previously it was x square with respect to x, the derivative written 2x, but now it is y square with respect to x, so the variable has changed. My derivative therefore will be the derivative of y square as per the same formula will be 2y, no doubt. But I just cannot miss the important component here to multiply, and that is dy by dx. So therefore, in other words, if I have any other function, say for instance defined in terms of y, say for instance I take the function 10y, and if I have to write the derivative of 10y with respect to x, the only fact I have to remember is the derivative of 10y as per the formula will no doubt will be sec square of y. But then I can't forget that I am actually given to differentiate the form with respect to x, and therefore I just cannot miss multiplying this then by dy by dx. And likewise for any other function if I come across defined in terms of y. In other words, just to summarize in all, like I would say that when you know that you are differentiating the term which is defined in terms of y, see that the immediate derivative of that particular function is written in terms of y following the formulas which we usually follow for differentiation. But then see that it is further multiplied by the important component dy by dx. We just cannot miss this important component dy by dx. So if you have understood this part very well, then now collectively use this whole knowledge in answering this particular question. What is the question? I read it again for you. The question is, I am given one implicit function x square plus y square equal to 16 and a simple question asked to find dy by dx. I very well understand that what I am given is an implicit function, and therefore the technique of differentiation is you just go on differentiating the terms as they are appearing in the given equation. So I will start my differentiation process. I will say I have to now differentiate this equation with respect to x. So therefore term wise, the first term I come across, I very well rightly see like which is the variable used for defining this term, x square. It is defined in terms of x. What am I differentiating it with respect to? The same variable x. So I am differentiating x square with respect to the same variable. So no complications here at all in writing the derivative. My derivative of x square from the list of the formulas I know is 2x. Plus, now coming to the second term, I read the term as y square. I can't forget that I am asked to differentiate it with respect to x. Yes, here is the alarm. So therefore I now realize that I am tackling the term y square in terms of y, but I am given to differentiate it with respect to x. Yes, meaning there is a difference in the variable, and if there is a difference in the variable noticed, as I told you all, we cannot miss that dy by dx, and therefore please follow the right way. Y square, as the derivative of x square was written to x, no doubt derivative of y square also will be 2y, but because of that difference we notice I just cannot miss multiplying this by dy by dx. So if you understand this particular part well, then certainly no difficulty at all in finding dy by dx. I proceed further. So equal to, what do I find given to the right side? 16, a pure constant number, where we know that the derivative of constant number is always 0. So the differentiation process has been completed. Now coming to the question asked. The question here is to find the value of dy by dx. Now please remember the important fact here is what I have to do is once I have completed the whole process of differentiation, I just have to rightly play with this equation now, just in assembling all dy by dx term on the left hand side of the equation, and I will see that all the other terms are taken to the right hand side of the equation. That's the only thing I have to do in deriving my value of dy by dx. So one important thing that I can do is, since I find that 2 is common throughout the equation, I would cancel that 2 and therefore will derive the equation in this particular manner. See the simple equation which I have got. And it is this particular equation which is going to give me the answer for dy by dx. And you will rightly understand, if I have to find the answer for dy by dx, certainly the term which is appearing in terms of dy by dx has to remain on left hand side. All the other terms from left hand side have to go to the other side. So it is this plus x which therefore will go to the other side minus x, and this will therefore now help me in framing my answer for dy by dx. There is another term, extra term which I see here, rightly has to be shifted on the other side. So my answer for dy by dx therefore will be equal to minus x divided by y. Now how much of differentiation has gone into this? If you see, it is only one step. But see that if you do not commit any mistake here, in this particular step, because what you have then to follow is nothing but simple algebra. Just shifting the term from one side other side and tactfully deriving the value of dy by dx. That is what you do in the later part of the solution. But make sure that you do not make any mistake here in differentiation. And that is the reason I told you all, differentiating, just be aware when you are handling the term which is defined in terms of y. More better understanding, here is another case before you. Again, if you rightly see, you see all x, y variables put together in defining the form. So therefore, again a case of implicit function and the question remaining the same to find dy by dx. And as I have suggested, I told you all that moment you come across an implicit function, see that the differentiation begins term wise. So therefore, I read the expression, the first term I come across is xy. How do I read it? X into y. So it is the product of variables. And therefore, for every product of variable, as you know, when I will start with the differentiation with respect to x, I will find that I have come across the product form x into y. How do I differentiate the product form? It is always by algebra of differentiation, the product rule. As per the product rule, the derivative of x into y will be the first term x as it is into the derivative of the second term. So derivative of y with respect to x, certainly dy by dx, not that over, plus, I am still going by the algebra, plus the second function y into the derivative of the first function x with respect to x, as we know always is 1. Now we are finished with the first term, plus, I am going term wise, plus the second term I come across, y square. It is in terms of y, but I know that I have to differentiate it with respect to x. So therefore I told you all, so therefore this is the sign that I have to be little alert. If it is y square, the derivative no doubt will be 2y. But as I told you all, we just cannot miss the term dy by dx here. Equal to derivative of 10x. The term defined in terms of x, I have to also differentiate it with respect to x. Derivative of 10x simply to be written as sec square of x. Plus, I come across the term y to be differentiated with respect to x. The derivative therefore is dy by dx. Now see the entire equation, how many places do you find the term dy by dx occurring? If you see 1, 2 and 3, it is at 3 places. What I have to do is, I have done with differentiation, but in order to give the final answer for dy by dx, I will have to just see that I assemble all dy by dx terms on one side and the remaining terms not carrying dy by dx are transferred to the other side. So if you see, the first term x dy by dx carrying dy by dx will remain on left hand side. Another term carrying dy by dx and another term with dy by dx is on other side. I will shift it, minus dy by dx, and all the rest of the remaining terms in the expression will move to the right hand side. So sec square x, and I have another term to transfer, minus y. Take all dy by dx factor together common here outside the bracket. This will therefore leave x plus 2y minus 1 inside the bracket equal to sec square x minus 1, and this will therefore help me in framing my answer for dy by dx which is asked. And therefore my answer for dy by dx will be equal to, what I just have to do is remove this particular part from here or shift this particular part. Where will it go? It will go in the denominator. So my value of dy by dx will be sec square x minus y divided by, as you see, x plus 2y minus 1. That's it. See how simple it is, provided you follow the things which are told to you. Go stepwise, differentiation and then assembling of the term. That's it. So now the concept here, another additional concept in differentiation, we read it as derivative of inverse trigonometric function. So after learning about differentiating composite function, then we learnt about differentiating implicit function. Now we are here to learn about differentiation of inverse trigonometric function. Now first again coming to the term inverse trigonometric function. Of course we know what inverse trigonometric function is, isn't it? Because we have already completed a session on the topic inverse trigonometric function. So we have rightly learned that corresponding to 6 trigonometric functions, we have 6 inverse trigonometric functions defined. We also know about the domain, codomain where they are well defined, and therefore, considering these inverse trigonometric function, let us now also learn how to differentiate this inverse trigonometric function. Now what method do we use for differentiating inverse trigonometric function? Now first of all, like, don't you think find that differentiating inverse trigonometric function would similarly become easy if we have again the formulas for differentiating them? So therefore, let us in a way first try to construct the formulas of derivative of inverse trigonometric function. Say for instance, I have a function y equal to sine inverse of x. The first inverse trigonometric function, I call it y equal to sine inverse of x, and I am given the question to find dy by dx of this inverse form. Now how can I differentiate this? Just in a way, trying to derive a formula for writing dy by dx of sine inverse of x. What I can try doing is, if y is equal to sine inverse of x, I can therefore write x as equal to sine of y. And if it is x equal to sine y, if I now try differentiating this equation with respect to the variable x, then what I therefore will get is differentiating the equation with respect to x. So x when differentiated with respect to x, the derivative is 1, is equal to derivative of sine y with respect to x. So the change in the variable, derivative of sine y no doubt is cos y, but then we multiply this by dy by dx as we learnt in the previous concept. So therefore dy by dx, and therefore I get my answer for dy by dx as equal to 1 upon cos y. But then very well know that this can be also written equal to 1 upon, if I use the trigonometric identity, then it is this trigonometric identity sin square y plus cos square y equal to 1 will allow me to write the value cos y as square root 1 minus sin square of y. And therefore what I finally obtain is my dy by dx equal to 1 upon square root of, though it is 1 minus sine square of y, I also know that I can replace sine y by x, isn't it? And therefore if I do so, my answer for dy by dx will be 1 upon root 1 minus x square, knowing that sine y is equal to x. See therefore what we have successfully derived is that if I have the function inverse trigonometric function given by y equal to sine inverse of x, the derivative of the function is equal to 1 upon root 1 minus x square. I can try doing the same also for the remaining 5 inverse trigonometric functions. The same method will go into. The right trigonometric identity has to be used here at this particular level, and if I try doing so, I therefore will be able to prepare the additional formulas or the list of additional formulas for all these 6 inverse trigonometric functions. And if I just view these additional formulas for you, the formulas would be like this. You can try using the same skill for deriving these identities. The method will be the same. But finally what you all will achieve will be these 6 important identities. So as you see, derivative sine inverse of x, as I explained just now, is 1 upon root 1 minus x square. If you try doing the same for cos inverse x, you will get, the only difference you will notice will be in that negative sign. The answer will be minus 1 upon root 1 minus x square. Imagine, it will be also easy for you all to grasp the formulae. The third one, derivative of tan inverse x will come 1 upon 1 plus x square, whereas that of cot inverse x will be exactly the negative of that. So minus 1 upon 1 plus x square. What will be sec inverse of x? Is 1 upon x root x square minus 1, and that of cosec inverse x, if you just compare with the previous, just has that negative sign there. So it is minus 1 upon x root x square minus 1. So this would be therefore the additional list of formulae we have to have at a credit. Now since we are doing a concept differentiation of inverse trigonometric function, we may have to use these important identities here in differentiating the forms. So let me now explain to you all how exactly do we use these formulas in differentiating inverse trigonometric function. Say for instance, I have the function y given by, of course if it is sine inverse of x, the immediate derivative from the formulae I will see that it is 1 upon root 1 minus x square. But imagine now, suppose if I have to tackle some composite form, meaning say for instance I find that the given value of y is something like sine inverse of 2x. Just compare this example with the formula we have written. The formula is for sine inverse of x. what we are given for differentiation is sine inverse of 2x. So, this makes this particular case a composite case. So, but of course, noting that since I have noticed that the function no doubt is sine inverse function, I know that my differentiation when differentiated with respect to x can be by following the formula. How? If I know that derivative of sine inverse of x, I know that derivative of sine inverse of x is 1 upon root 1 minus x square. It is only that I have to notice that what is going in place of x now is 2x. So, I have to see that I do the same change now when using the formula. So, when I am writing the derivative of sine inverse of 2x, I have to no doubt use the same formula, but see that the change is correctly adopted. So, sine inverse of x if is 1 upon root 1 minus x square, then the derivative of sine inverse of 2x will be 1 upon root 1 minus 2x the whole square. So, it was x earlier, now it is 2x. But since this was a composite case, I just cannot miss multiplying this then in turn by the derivative of the next function in sequence, and that is 2x. What we know, derivative of 2x is 2. And so, my answer for dy by dx will be 2 upon root 1 minus, I may write it as 4x square. So, see the technique. I am rightfully using the formula which I have included in my list, which I have already derived, but I am using it now for differentiating all composite forms. So, this is one example which I tried to explain to you all on differentiating inverse trigonometric function.
Prudent Scholars, powered by Lupin Pharmaceuticals.